It just started up. Hope maybe it caught me talking about how I misstate what I talk about a lot. How are you doing, Ben?
Doing well.
Happy
I'm in a very
Happy
quiet house
Friday.
right now. Yeah,
Wow.
I, uh,
Wow.
I, my wife had booked a camping spot, uh, 50 minutes drive up the road, and now I'm hearing us in echo, so I'm gonna mute that. So the tube is working. Yeah, so my wife and kids are camping up at the beach, and
And you
and
had to stay behind.
I went up there with them on Tuesday evening and set up camp and stayed the night there and worked worked remotely from there for a day and realized the internet access through her phone tethered. Uh, my phone, the company switched from one ginormous provider to another, and probably to save money. But the net result was I had terrible internet access on my cell phone, so I had to tether to my
Oh,
wife's, and it was even then it was really slow. So I thought it was fast enough for the Zoom calls for work, um, and fast enough to get Fusion 360 running and basically do some stuff. But I realized I would just prefer to work from my home office and not have trouble. And I knew that Friday morning is our stream time too, so I want to make sure
right.
had a good connection. It's bad enough on the best of days. So here I am in an empty house, and everyone else is at the beach. I'll go back
Very cool.
tonight, hang out with them tonight. So
Right.
yeah. Anyway,
So,
too much
and I had
information.
asked you about your shirt. That's the Australian flag you're wearing today.
It is. It is. I'm feeling nostalgic for my family, and my dad bought me this T-shirt when I was leaving Australia in 2011. So I don't wear it all the time, but it's a pretty good quality shirt. So
And the star represents what?
this, okay. So obviously the Union Jack, like Hawaii's flag, it was originally a British settlement, so that's why that's there. The 7-point star is the seven states or territories of Australia. So New South Wales, Victoria. I'll just go I'll go clockwise from 3 p.m. around.
Ha.
um, New South Wales, Victoria, Tasmania, South Australia, Western Australia, Northern Territory, and Queensland. And then this here is the Southern Cross
Southern.
constellation, which is very, very
Right.
bright and prevalent in the southern hemisphere sky. You can't see it from up here, so I
Right.
missed that. But that's okay. We've got the drinking gourd,
What's the drinking gourd?
the Big Dipper.
Oh, okay. All right.
You were saying what? Well, I don't remember the star names. You know the star names. Was it
I
Cygnus?
used to know them. Yeah, like I remembered that the second one on the end of the handle is actually a double star, but not a true double star. They're just in
Oh,
alignment.
right. Yeah, one's sort of behind the other,
That's it. And it
and
was
they're
an eye
actually a
test
very long
early
way
on.
apart, right?
Yes, they are. Yeah. But it was supposedly an eye test, early in the early days. If you could distinguish the two stars, you could see a degree of separation or something. I forget what it was,
We
but
had
I
that
forget
just a
those star
few.
names.
Yeah, we had that just I think 2 months ago. We had two of our planets cross very close in our night sky. Did you see that? It was, I think,
Yeah,
Jupiter and
I
Mars,
yeah, I
Jupiter and
forget which
Saturn.
two, but they
Yeah.
they they had a couple of near occlusions. Yeah, it was very cool.
So,
So
what am I looking at here, Bill? You've got something open here with some. It looks like an emulator, and this is something. So just to tell everyone, uh, this is why you need to get on our Discord. There's interesting discussions, but some of the people in the group are doing some pretty amazing, clever work, and this is one of them, right? Tell us about this. What are we looking at here?
right. So I had asked Frank Buss programmer Frank off of our Discord, and now I need to actually find the screen so I can scroll. Here we are. So what it is I wanted to put one of these small vacuum fluorescent displays off of a 6502, and you've seen this display before.
Are you're well, I'm not seeing your camera.
Yeah, I covered myself up.
It's obscured by the shared window. Yeah, there you go.
So there's the vacuum fluorescent display. This is available for Mouser, so it's a contemporary part. And I wanted to hook it up to the 6502 single board that I've been working on, but I didn't want to do any programming. I just didn't want to do the programming. So I asked Frank, I said, hey, do you mind doing the programming? I'll even ship you the parts. Actually, I threw it up to Discord, and he was the first to respond to it. So again, watch our Discord under the project thing, project subdirectory. We are talking about projects. And so Frank worked up an simulator that simulates the actual vacuum fluorescent display using a simulator he already had, and I don't know the specifics. Frank, if you're out there, tell us. He actually mounted it in the Discord, but my memory's poor. I forget the structure he used, but this is a web browser, and it's actually showing the single steps. My memory is you can single step this, maybe? Hang on.
So
yeah, there it is. Yeah, I can space bar it and stuff.
Yeah. Okay, and you can break and continue. So this is one of the reasons why we loved the 8-bit CPUs that are pretty much entirely static. Modern CPUs, to get everything really, really small, so if you were using an STM32 or something like that with an ARM Cortex M4 or M7, that's all CMOS, and chances are, like, we don't know the exact, memory that they're using for scratch pad RAM and things, but you buy a microcontroller today and it might have a megabyte of internal scratch pad RAM. It may actually be implemented as dynamic RAM that has a DRAM controller that makes it behave like static RAM, so that your software doesn't know any different. But the deal with that is you may not be able to halt the processor down to a 0 clock, whereas these older CPU architectures like 6502 and even 8051s and others like that, Z80 was the first one that had its own built-in DRAM controller and DRAM refresh and all of that. So it's not able as easily to go. In fact, I don't think you can single step by halting the clock in a Z80. You have to use a debugger. I may be wrong on that point. But with 6502, you can actually just stop the clock.
On the 65 CO2 you can. On the old O2s you couldn't.
Okay, so when I was in college, it was a CO2 that I was using. So that must be. Yeah. But that's the beauty of some of these things. But it's also a good reason to have a software. I mean, Frank's calling this an emulator. I'd call it a simulator.
He just posted. He wrote this as he uses SDL graphics library, and this is WebAssembly is the name of the framework that supplies this.
Right. So, and he was describing in the Discord what is WebAssembly, because it's reasonably new. Right. It was new to you and me when he started talking about it, but
right.
WebAssembly, what it amounts to is I'm probably butchering the statement of what it is, but it's like modern web browsers all support a common language runtime, which is WebAssembly. So you can write, and maybe it's a plugin that some browsers have to have installed to support it, but basically it's like hardware programming that runs in any browser on the client side.
Right.
So it's like writing Java. It's a replacement for JavaScript. It's probably
I wonder if faster. It's HTML5 or something under the covers.
Yeah. Yeah.
So
But the
yeah,
cool thing is, so what Frank's built here is this: you can upload any assembly language file for a 6502, and it'll compile it to WebAssembly and run it in the browser in WebAssembly.
and he made a 6522 component and hooked it to the vacuum fluorescent display component. We lost you there. But yeah, and Frank's saying he believes it's pre-installed in Chrome and Firefox. So, and we've lost Ben there. We can hear the beeping of his Skype, and it's 11 minutes after the hour. That's when it seems to happen. So, but yeah, are you back? You're back. I can see you
I'm
moving.
back. Yeah, I find what I do is I have to open the Google speed test, and it's like kicking it in the guts.
Wow, that's interesting.
Yeah. So
So
did Frank write the program? Frank wrote the code here and is running it to emulate the display. And he wrote this display emulator and even did it with the little dot matrix. So I'm impressed. That's a lot of work to build all that in just a few days.
yes, it is, and it uses the standard 4-wire interface. I guess it's 6 wires, but for the little LCD displays you see all the time. But and I don't know if he already had a digital code for a display and he just redefined it to be 2 lines by 16 characters, or if he completely wrote the the display area, to scroll it like that. But yeah, this is why the world needs programmers. You may hear me say, programmers, but a hardware engineer can't do a thing without a programmer, and
Yeah.
I used to do both, but I don't these days.
We need each other. We need
yes,
teams.
we do.
And this is
do.
this is a hard lesson for me in my career. I've always wanted to be the lone wolf and do everything myself. And you just can't get anything done that way. It doesn't work. Not in this world. You've got to be able to team up and share ideas and be willing to compromise. And
Right.
it's hard for an arrogant person. I'm
That doesn't wear a turtleneck.
I'm being humbled the more I go through life and realizing that you got to be a team player, or nothing magical happens without doing that.
That's and I did find that early in my life, like the Commodore era, my version of leadership was I led from the front and just assumed people would follow me, and later I had to learn about true team building and team exercise and the value of the team. So I had to learn that with maturity, I would say. So that was an important lesson.
Because when you're a smart person and you're capable of doing things like electronics engineering and also something else I've learned is there are plenty of other smart people out there, easily smarter than me, a lot of them who don't know what electronics is or about, and that's not because they're not smart, it's because they chose something else,
Right.
So tell us about this though. To connect that Noritake Itron VFD, which is,
right,
they're absolutely beautiful, but they're kind of expensive, right? Because there's a lot of.
I want to say it's $15, something like that.
Really, that's all? That's not bad.
Yeah, I had the link in the Discord channel. It's I'd have to go look.
So, but a 6502 is a CPU, not a microcontroller. So
right.
Obviously Frank has built into this emulator some other I/O type stuff. How does all that work? Is it just memory mapped and bit banged, or does he have a 6522 emulator in there?
That's a great question. Yeah, he's bit banging the 6522 as if it's a real 22. He sent me the code. I would have plugged it in, except I realized I didn't have a 65. Actually, I have a very old 6522 in stock. It's 40 years old. I'm not plugging it into anything. Yeah, it's over in my bin of real old parts from the day. But so it literally is meant to run on a 6522, and he would have had to emulate RAM and the ROM area and fill the ROM with the hex file and everything like that. So again, amazing amount of work for the short period of time.
That's awesome. Now this emulator is just running the code, and you can break, you can continue, or you can reset. But it's also got single step. So this is actually becoming a web-based debugger. That's what that is. And that's actually an insanely useful tool for
It's how I learned code. It's how I learned code was on a Rockwell System 65. We called it the Rock Box. And, you know, Rockwell was one of the people that licensed the 6502 early on. And I would drag this thing home at night and bring it back to work in the morning. It was huge. I needed a Lear Sigler ADM 3A terminal, one of those real cool terminals like you see on the Loki show. And and the biggest thing was single stepping, learning what it does at a minute level of the code. And so, yeah, you can single step it, find out what you did wrong.
Well, on that, if you reset, I think the way that this emulator is working now is it's not highlighting the line of code that you're in. It just gives you the program listing, right?
Right. That's what I'm assuming there.
It does tell you the program counter, so you will know where you are. So, for example, if you reset, if you hit R, it puts your program counter back at the user program
8,000. Yes,
8,000. And then if you single step with a space, where does that put you? 8,001.
8,001. So it didn't do the reset vector. It just started at the location pointed to by the reset vector.
Okay. Yeah. So a little bit of hand waving there, but that's okay.
Yeah. Right. But down here is the reset vector at FFFC, and you see it points to 8,000.
Gotcha. So go up to 8,000. Scroll up. There's 8,000. So the 10,000s is just those are non-memory locations. Those are just equates for labeling in the assembly language code.
And then he sets the origin to 8,000 here.
Yes. Right. And so it's dealing with pins. Now he's got some nice comments in the code there too to say init display, and it does a jump subroutine LCD init, so you could scroll down to the LCD init label, and that would probably set all port pins to output in 6522. So he's not only created a 6502 emulator or simulator, but also 6522. Now, my question is this, Bill, on this web page, can we right-click and look at view the source to get any kind of glimpse of what the WebAssembly looks like? Or is that...
So I think the WebAssembly is right here, right? The assembly is here. So this is this is like a listing file.
That's your 6502 machine code instructions and the assembly mnemonics shown beside it. Right. So you see
with the actual code there in the middle.
So this is a store external. So this is sending a byte out to the peripheral 6522 E002. So the store external command, the store external or STX instruction on a 6502 is that 8E, and then the following bytes, which is little endian, because the O2 comes first, O2E0, right?
Which screwed me up for years because I was byte swapping phone numbers. If the phone number was 1234, I'd have to work hard not to dial 3412. Just because I looked at listings so much in my earlier life.
Your brain got stuck in little endian.
My brain got stuck in India. Yes, it did.
That's funny.
Byte swap mode.
So what I'm just wondering though, if you scroll near the top, where scroll to the top of the page above the 6502 assembly listing and right click and do view source. I don't know if it may. I don't know enough about WebAssembly to know, but if you right click in there and do view source.
All right, so Frank has chimed in on this. So but he said you can see that some Java and stuff, but he said he could display the source code line as well in single step mode. So he said he can actually recode that.
Yes,
But
that would
the
be
actual
super
web
useful.
source, yeah,
You want to see exactly where you are in which line of code. Yeah. So
there's the WebAssembly stuff.
okay,
Yeah.
so there it is. Load WebAssembly application. Scroll down a little. So actually so that's JavaScript, and the JavaScript is loading the WebAssembly. So there's this index.wasm file. That's the actual WebAssembly, and then that's being executed somehow. So I wonder if we could probably find index.wasm in the address bar of the URL. It may not be, like, the server may not be configured to allow that to be visible.
Right.
But if it were, we could take a look at what the WebAssembly.
Yeah, he's got it pointed just at a directory, and it's defaulting to something. Yeah.
Yeah.
So very cool. Yeah.
Yeah. So anyway, that's really neat. Everyone should check that out. And
it's up on our Discord channel, and you know, we wouldn't mind maybe getting a project going where we can all contribute to it. You know, other projects have started with less. Yeah.
That's right. Yeah.
So
on that, I'm so close to finishing my FPGA board with the ESP32. We'll probably look at that as a final live design review next week, but I'm getting very close to being able to order boards, and once that project's done and out of the way, maybe we could do a new one that's simpler but is maybe a 6502, or I mean, you've got your board also, of course, that you're working on. So, but I'm just thinking there's something we could do for the Coriolis effect. We could have a Coriolis board. I don't know if everyone on the Discord would be interested in that, and we'd obviously make it open source and let different people in the group contribute, and maybe if anyone's interested, we could go in and get a bunch made and play around with them. We could get Frank and Mike Fikes, who are awesome coders, to develop some software with us. What you running there, Bill? You've gone into the background on a C128.
There we go. So yeah, I was hanging out at Nibbles and Bytes, and somebody asked me, how long does it take to drop out of 2 megahertz mode or go into 2 megahertz mode? I should have set it for single step. Hang on.
So you're issuing a command there on your 128 to change clock frequency.
Right. I don't know if you can hear me, but I'm doing it with a poke, but it's not working as reliably today, and I don't really want to dink with it to figure out what's going on.
So that's what we're looking at on your tech.
Yeah. Hang on.
And you're triggering, you've got a...
Yeah, I'll show you the trigger here in a second. But I'm issuing basic
for that event. And you said you weren't a programmer.
No. And it's not grabbing it right now. So what I wanted to show though was
it did display it for 30 seconds.
It did, and then it jumped. Yeah, and I don't know why it's not taking it. I suspect there's a line loose.
Do you have to reset the scope to enable retriggering?
No, it's hey, thank you. It did do a single. Yep.
There it is.
Yeah.
There it is.
So here the
captured
clock is already in 2 megahertz mode. And you can see the I/O cycle. So what was cool about this, let me find the web page to manipulate this. Too many web pages open. Is that I have, in my scope, I have the ability to do a complex trigger function. Let me get some things out of the way here. So in this case, I told it logic, which you can see right here. But I could also trigger on setup and hold. I assume a setup or hold violation, or if a rise time or fall time. Almost all of these have, if it's too small or too big, you can trigger. So you can do less than or greater than. But what I was able to do here is combine digital inputs. So I said, hey, define the inputs. Well, I want the clock to be high, which is when it's a valid write cycle on the 6502. I want the chip select for VIC to be low so that we know we're writing to the chip. I'm actually ignoring the state of the 2 megahertz clock, and I'm triggering on both setting it high and setting it low. But I could have qualified the D, the data bit, 0 or data 1. But then I brought in the bus connector. So there's 16 discrete bus wires also on this. And I hooked them to D4 and D5 and said, okay, when the address is 30 or a 3 anything really, to bring that in and include that in this trigger word. So if it's a write with a VIC chip and it's writing to this register at 3 something, then it would go ahead and display it. So hang on a second, and it just triggered again. But I wanted to try and capture. So what happens?
So you have a separate, the 2 megahertz is a separate 2 megahertz crystal.
No, this all runs from an 8.18 megahertz crystal, and up top is our, and it's run through a phase lock loop that's like a 3/5 divide, something like that. And up at the top is the standard 1 megahertz. This is what runs out to the bus that all these Commodore 64 things are compatible with.
Yep.
And then we have the clock that goes to the 6502. Let me see if I can slow it down. Let me see if it'll cooperate here. So I'm doing this with just a basic poke.
There it is, yeah. Yeah. So the actual, the phi didn't change, but the other clock is changing.
Right,
and
right. And so
it toggled. It went slow and then fast and slow and fast and slow again.
So it went slow because it's an I/O cycle. So I clock qualify all I/O cycles happen at 1 megahertz. It's only a pure processor cycle and talking to memory where we steal the cycle from the 40 column VIC chip. So this only works in 80 column mode. So I'm actually on my 80 column monitor. When you're in 80 column mode, you stop splitting the bus between the 40 column and the processor. You take them both for the processor. So the processor is already running at 2 megahertz. It's just only getting half the time to do it. And so what happens is you see right here, this is the cycle that said, hey, that's an I/O cycle. One more clock of the 1 megahertz, and then it dropped to 1 meg. So that was the answer we were looking for. They said, well, how long does it take to switch back to 1 meg or 2 meg? I'm like, near instantaneous. I almost thought it'd be instantaneous, but what they probably did was probably pipelined this so that they didn't try and switch to high-low speed clock on the fly. They probably put it in a flip-flop and said, on the next start of a cycle, go ahead and acknowledge whether it's going to be a slow speed or high speed. So now what is, oh, I see. So it's catching a glitch here on the edge, and I could probably go into my trigger specification and say, by the way, it has to exist for more than 10 nanoseconds.
Right,
or
filter
something.
It somewhat. Yeah.
Right.
Yeah.
So the interesting thing about this is when, you got to love the 80s, right? When else could you double the performance?
Best music.
And you can double the performance of a computer, almost double it. It wasn't quite, but you could almost double it by just going up a single megahertz, right? Nowadays, if you wanted to double your PC, you'd have to go up 3 gigahertz, or some crazy amount of.
Yeah.
And that means your memory and all the other things that go with it would have to double.
You need a power. You need to go from a 500 watt to a 1 kilowatt power supply.
Oh yeah, it's a system, and that's the whole thing. Is the system's only as fast as its slowest link. I equate system design to holding a pan like a baking sheet of water, right? And it's about balance. If it's too tipped, your processor runs too fast. You're waiting on memory. if you just missed a memory cycle, maybe you're now in a wait state because you went a little too fast. Slow down a little and you'll actually get more done. That's the symptom of a system that is hitting a wait state that you don't want.
True. And this is also why we now have like very complex CPU architecture, like multi-stage, or pipelined execution, prefetch, caching. All of that comes into how do we keep the CPU fed while the whole rest of the system has to go off and do different things.
Right.
And it's a fascinating topic.
So I do have one more thing to show you here. Let me see if I can expand it. I just happened to find this while looking around the other day.
Oh.
And this is so old that I used the software that PC board manufacturers have you use. Let me see if I can make this bigger.
Oh, you mean you use some sort of free circuit board?
Yes. Yeah, this is probably for PCB.
Okay, right. Or PCB 123 or one of those.
Or something like that, yeah. And look, you could see the number of mistakes I made on it and stuff. It took weeks to arrive. It's not like JLPCB or PCBWay. But what this was, a friend of mine worked in the cardboard industry, and they needed to align, I believe, a box cutter. And they needed to align the cardboard before doing the cut, and he wanted to superimpose crosshairs onto an NTSC stream. So that's what this did. Is this takes two through VNC connectors. It brings in two NTSC signals, has the FPGA that has it's got an LM1881 sync separator on it. One of my favorite parts. You can't do sync separation yourself easily in the old days. Try and tell your horizontal sync from your vertical sync and whatnot.
So we're talking video signals now.
Video signals, right.
Composite.
RS-170, yes.
Yeah.
Yes. And I ran it to a CPLD, gosh, I can't remember the family name, and it's too dim to... It's a Max 2, probably, FPGA, CPLD. And then the pots are how you control the horizontal and vertical of the crosshairs. So basically, without a microprocessor, I superimposed crosshairs using just FPGAs.
So it's just a video signal
some
from
jumpers.
A CCTV camera,
right,
mounted over some conveyor belt.
That's right.
And then all they wanted was crosshairs put on the video. And
they wanted to dial them in, and then from then on use the crosshairs to line up the cardboard before hitting the cut cycle, I believe. So it was interesting. Yeah, I mean, there wasn't really processors that could keep up with NTSC signals back when I did this. I did this like 15 years ago.
Right. Yep.
So things were still running in the megahertz kind of for then. I mean, for control, the controller of the day was the 8051, which you mentioned, which a friend of mine said, if you looked at an old soda machine, that's an 8051. He worked for Mars, and he said one of the hardest things he ever had to do was make an 8051 work in a soda machine at the end of a dock plugged into a lone extension cord, all the lightning and environmental variables, and how to keep his 8051 working. And resetting itself and watchdog timers and stuff. Yeah.
This is the other reason we get all nostalgic, I think, is that there was that time period where you'd really have to hack and bum instructions to get everything to work at full speed.
Yeah.
And you could. So it's like my computer systems instructor at college when I was learning with a 6502, and I was complaining, 6502s, because I'm talking early 90s when I was at college. 6502s are all out of date. This is not current technology. We should be using a 16-bit microcontroller or something like a 8052XA or something. And he's like, Firstly, the college bought thousands of 65CO2s so we could keep this project going.
Right.
And then,
Right.
and secondly, this has everything you need to learn the principles you need to learn.
Yeah.
And so I grew
And
to appreciate it. But in telling me that, he said before he became the teacher, he was retired from industry and got the teaching gig at college. And he worked for a company that did high-speed printing for newspapers. And they did these drum printers. So a drum printer has a big stainless steel drum where all the characters of a fixed font are molded or machined in the exact size, and that maybe they have different sizes around the drum, but normally it's one big drum, the width of the paper.
right.
It has
Lithography. Yeah.
it has all the way, no, not lithography. This is mechanical. So all the way around the drum, it has in the steel drum, it has the letters of the alphabet all the way around and all numbers. So, and the drum is so many columns wide, big enough to make a full-size newspaper.
Right.
And it
Right.
will print one page in, fractions of a second. So these drums are spinning ridiculously fast, and they're machined to be perfectly weight balanced. And each rotation of the drum, it has a hall sensor on both ends, and the drum was controlled by an 8085, which is a successor to the 8080, which is a right around the same time the 8051. 8051 maybe came out just after the 8085, which is the CPU that was used in tons of CPM computers of the day. It was the main competitor to the Z80, right?
Right.
And he
Right.
said they had maybe at 2 megahertz something like 50 clock cycles between interrupts for each revolution of the drum, and the CPU had to do all like that, run through its entire code in just 50 instructions between interrupts.
Right. 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 Including the time it takes to interrupt. Yeah.
Yeah, and every revolution of the drum was an interrupt, and
Right.
and these things were printing newspapers, and you've seen the newspaper presses, how fast they go.
And so I did a digital scale back when I worked for Pennsylvania Scale before Commodore, where the application was to try and determine how much ink is landing on those papers, because they'll start getting too heavy, and they don't want any more ink than they need. They also don't want too much water in the paper. And so that conveyor of newspapers coming by would go over a load cell, and at any one moment, so we ran a filter for the motion and everything, and at any one moment there'd be an integer number of newspapers on the scale. And the trick was, well, is it 12 or 13? Well, it's 12 or 13. It's not 12. And so realizing if it's an integer, is there too much ink or not enough ink or the right amount of ink? So that was one of my first projects that I did, where I converted an existing application, a digital scale. I rewrote the 6502 code to do this on-the-fly averaging, and we did all in floating point back then. So we had some pretty fast floating point. We could do a divide in like 50 microseconds, which was humming back in the day.
That's really fast for really floating
That might be a
point.
multiply, and maybe 100 microseconds for a divide. I forget, but we could do all our math, and we did full Laplacian transform and everything. We'd get it done in a couple hundred milliseconds.
That's insane. I didn't think that
Yeah.
was even possible on a 6502.
Oh, we had a bitchin' little floating point thing. Hey, so somebody mentioned PLD extractors, which I happen to go and grab. I'm showing them right here. And that reminded me to show you the kind of packages is. This old PLD package is called a J-lead. And this is what allowed me to do through-hole back in the day.
Yeah.
Because you could get a socket that was through-hole, and then the package itself can either be soldered directly to the board, these little J-leads,
Yeah.
can touch the board.
That's a PLCC. It's a JetX standard package, and it's still specified even in IPC 2581. Oh, sorry, that's the wrong spec. 7351 is the standard.
I
And,
can't remember the.
Yeah, normally those are soldered direct to the board, but the sockets you can still get. I've got a few. There are some parts. They were really popular for 8051 derivatives for a long time.
Yes,
and CPLDs.
Right. Oh, so do you remember the 8186?
Yes.
Yeah,
that was kind of
popular.
The weird in-between one, between the 8086 and the 286. That's the one everyone kind of ignored, except for industrial applications, right?
Right. It was kind of more like a microcontroller than the others, so you just happen to remind me of that. Maybe I can. Let's see if I can share it real quick here. So basically what they did on the 8186 is they said, there's a certain amount of stuff you always need. And like I/O chip selects and stuff and wait state generators and whatnot. It had a DMA unit.
So it was a CPU, but it was sort of more like a microcontroller in that.
Like a microcontroller.
The chip select unit. Yeah.
Right. So, if you ever see an 8186, that was like halfway between an 8086 and an 8051. It had stuff built into it. Had a programmable logic interrupt controller.
Those were used in some early synthesizers and other musical equipment, if I recall. And they also had, and then right around the same time, Intel had this other. The 8051 was so successful. They said, "Well, we've got to do the same thing, but in 16 and 32 bits." And so they came up with the 8096, which was a 16-bit microcontroller family.
Right.
So it's, but no one to this day could ever rationalize why they completely did new instruction sets for each and every one of these. And then they did the 80196 and 296 families, which were 32-bit RISC microcontrollers. They had a very different philosophy. I think they must have employed a bunch of completely different people just to work on those, because they were so different than anything else Intel put out. They actually solved all the irritating problems people hated about the x86 family,
right?
The segmented addressing and all those ball aches that make it a pain in the butt to do any kind of low-level programming for. And philosophically, there are people who argue in favor of segmented addressing, and there are some reasons why they had it. That's fair enough, but it meant it wasn't comfortable for control systems where you just wanted high execution speed and simplistic addressing and memory mapping and all that. So they came up with the 196 and 296 families, 32-bit RISC, and they had flat addressing, and if I recall correctly, and no multiplier divide or anything like that, but super, super fast. And those ended up on RAID controller cards everywhere. So a lot of the Adaptec SCSI cards from the 90s have those
to calculate the Hamming codes and fire codes and whatnot.
Well, and also do the ECC or parity.
That's what I'm talking about.
Split up the data and keeping track of things and doing it in a way that actually increases performance.
So do you remember the TMS 340 series by Texas Instruments? It was a DSP. It was like a RISC. And I actually did a project for Cray Research back in the 80s. And Cray was like it. It was like...
That's the supercomputer.
That's
the one that made... what were the movies Cray was used in? It was used in quite a few.
Seymour Cray.
Awesome movies.
right?
Yeah. Anyway.
There's a picture out there. Somebody got a picture of me licking a cray one time. I mean, it was just like it was a religious moment for me, right? But the application was that they had these SMD based disk arrays. God, I'm trying to remember the name of the company. It's where Seymour Cray came from. Geez, I forgot the name of they made the big disk drives, but they were the big multi-platter things that you dropped in, but they were using the Cray as a disk tester. So it had to be the most expensive disk. That's how they would find bad sectors and whatnot. And so what we did was a box that sat between. You would unplug it from the Cray basically, and plug it into this box, and it would exercise all the SMD commands, which was the name of the bus back then, to do the testing of the multi-platter stacks, instead of having a Cray sit there and do it. And this was for the oil industry, actually, so they could go back to trying to find oil with their Crays rather than test their disk drives with them. God, if anybody remembers the name of that, where'd Seymour Cray come from? He came from not Winchester. It's, but I'll probably think of it by next week. So, anyways, enough of that. I've got enough screens open. That's what I'm saying. If somebody else wants to do it, every screen I have is full, and I'm trying to do a broadcast, which is why I stutter a lot and things. So, hey, can you show us state machines?
Yeah. So I actually. I forget who it was. Someone on the Discord suggested a free state machine editor that's been done in Java and Python. Not Python, Perl. Is this FISM? It's actually pretty cool. I would. This is just my personal preference as a product manager type person. I would like one application to just launch, and then give me buttons to export VHDL or Verilog from the image. But the philosophy of the program is the other way around. Most people develop state machines directly in language, because that's the value of the language, is you get to describe what it is you want to do, and you don't have to do it graphically. But this FISM, let me move that up because you're down a bit further. So this is it. Actually, that's full screen. I don't want full screen. So basically, this is just one of the examples, but you can create a state machine. You can come in and you can define states and transitions, and it draws an image of it. So the value of something like FISM is not so much designing the state machine, it's defining it, but getting a clear image. Getting that bubble diagram actually helps you understand that you've included everything. It's kind of a way of checking your work and verifying visually that you've designed something correctly. So what we're looking at here is a 4-state state machine. There's a default state, which is idle. That's the reset state, and that's given the double circle as part of that. If I double click on that, these are the properties of the idle state. You set up its name, what type of state it is. You can give it inputs and outputs, and they're just these end up being signals that are associated with the actual state machine in your hardware. So when I synthesize this after exporting it or converting it to VHDL or Verilog, these will be the signals that come out of my block or go into my block. And these are the things that can, on a rising or falling edge of a clock or a reset, can actually be used to combine that logic and change the state of the system. So this will generate more and Mealy machines. So you can actually have registers. And you can modify, of course, that afterwards in the code if you want. But you can have the registers after the state or before the state. The default is the registers are at the end of the combinatorial logic for setting states. And state transitions, the little arrows. These have equations and values. When it's that value, it's going to go from the state that it starts at to the state that it finishes at. So it's all pretty straightforward and easy to use. We look at you can look at all the transitions, look at all the properties of the whole state machine in one batch and set things up here. And you can see on the state machine, the global state machine tab, you can click the reset button and it gives you a reset signal and a reset state. So that adds the reset to the whole thing. You only want one reset. It doesn't make sense to have more than one reset. So, and then you can define, is it a negative edge reset, positive, or a value? What's the reset state? Now, this is interesting. If you say all zeros or all ones, it's going to reset every flip-flop in the generated state machine to all zeros or all ones. But that's actually also going to overly complicate the state encoding. Right. And add additional flip-flops to the overall state machine during synthesis if you want to do that. But for some types of design work, so if you were doing high reliability FPGA work, you want a reset to put the whole system in a predetermined known state that's predictable, that has no undefined outputs.
Right. You want to have every state defined. If you get into an illegal state, you want to have a plan to recover from it.
Exactly. So that's where it comes down to state machine encoding as well. States can be encoded. If you think about it, a state machine is like a very fancy counter, but the encoding of that counter can just be straight up binary, and that reduces the number of flip-flops. So if you're working on a simple PLD or even a CPLD that has only a certain number of macro cells, and you want to be judicious with your use of macro cells, you can leave it to the default encoding, which will use binary and will be optimized for the lowest number of flip-flops. But if you're doing high reliability systems, you might want to use something like one-hot encoding. One-hot encoding is where the states of the system are defined by a single bit being 1 in the register bank that holds the state of the system. So maybe you have 8 states in your system. One-hot encoding for 8 states requires 8 flip-flops, because 1 will be set to 1 while all the others are reset to 0. And then during the next state transition, a different flip-flop becomes a 1 and all the rest get reset to 0. Right. So that's more complicated and requires more flip-flops. But you need that if you're doing high reliability systems, because then the state machine can be defined to detect an illegal state. If more than one flip-flop is set to a 1, that's an illegal state. It's easy to detect that combinatorially and issue a reset command to the whole thing and start again. And you need that for things like aerospace, because your FPGA or CPLD may be in a satellite and it's out of the protection of Earth's atmosphere, and it may fly under the Van Allen belt, and radiation is imposed upon it, and gamma rays or other cosmic radiation can hit the silicon and force a flip-flop bit to go from a 0 to a 1 unexpectedly, and it puts the whole thing into an unknown state. You have to be able to know that it's in an unknown state, detect that, and force it into a known state.
Right.
Which typically your idle state. So for that reason, when we're designing state machines for high reliability systems, we use what's called one-hot encoding, and we explicitly say, what do you do if the state becomes undefined? Right. And that adds additional combinatorial logic to the output of the state register that says it's basically a big XOR gate, and it says if only one of these flip-flops is 1, then that's okay. But if more than one of them is 1, then let's reset the whole thing.
Right. Right.
And that goes in. So we define inputs, outputs. The reset and clock inputs are added there, and you can add additional multi-bit inputs. So your state machine may be doing something to multiplex or detect an address. Maybe you need a whole address segment, like the upper 8 bits of an address bus would come into this, and you'd use that to determine what state this thing goes into. So it's just super cool, and all of that can be defined, and what the outputs of the state machine are. So we can actually output, flags, and the state machine register outputs the state bits. So the actual state vector is one of the outputs here, and that's often a useful thing. And then what are the transitions? So anyway, all of that to say, it then builds the diagram, and you can move things around and adjust it. But once you've built that and saved it, the export here, I wish they'd put the VHDL and Verilog here on this menu, because that would save me the hassle of going into the command line and running a Perl script, which to me is a pain in the butt.
Right.
But you run the Perl script, and it generates. So where's my command line?
What did you have to do to make this run? Did you have to run this in the Windows subsystem for Linux, or what did you end up doing?
It will run in that, but the main graphical, the GUI for FISM just requires Java. Java runtime environment. On this computer, I have Zulu, which is a more commercialized version of that has higher security. But it runs with that. It's fully compatible. And then that's just to generate. That's the graphical editor for generating the state machine and the bubble diagram.
Right.
But what that gives you is these files, the FZM files, and those are XML. So if we look inside the FZM, it's just an XML file that defines the states, the state transitions, the inputs, the outputs. All that stuff is just defined in this XML file. But then they've given us this Perl script, fism.pl, and by default it's Verilog, but if you use this language switch and say language VHDL, it'll generate VHDL. And so you put the input file and you put the output file, and it turns that state machine into code. And then of course you could take that code and insert it into your FPGA design in whatever FPGA tools, synthesis and simulation tools you're using. And so this is the Verilog version. So Verilog, we always define the top of a Verilog module is all our inputs and outputs. So obviously inputs for clock, reset, go. Go is one of the state transition inputs. It takes us out of the default idle state. On a clock rising edge and after reset on a clock rising edge, if go is at 1 on a clock rising edge, it transitions out of idle to the next state, right? So we define all our signals, and then we define our outputs are the DS output, flag output, and these are registered. And then output register regdp out, that's our actual state. The current state of the state machine is those 2 bits. This is a 4-state machine, so we only need, with default binary encoding, we have 2 bits for the encoding. 0001, excuse me, 1011.
You're right.
You can also do, some state machines are gray coded as well. That's another option.
Right.
Yeah, so the state bits, these are our state names, and we're using 4 bits internally to define those. So this just means it's a 4-bit binary number, and these are the actual state IDs. But the register output of those, the way this one's designed, they've added an extra bit to get that encoding. So internally, it's using 4 bits, or actually 3 would be a minimum, but we're only outputting 2. And then internally, we have a 4-bit register for the state and what's the next state. So we're already using 8 flip-flops here for this state machine. And then the main state, so this is called a case statement, and we do the same thing even in C language. If you're doing in a microcontroller, if you're coding something, as we often do, using a state machine, when you have multiple tasks and you go out to do different tasks and come back, or maybe your main program loop goes out and does different tasks and comes back based on what's enabled by other external input or interrupts. And so you have a main program loop that just comes back around at the very beginning. The key difference here is we're not sequentially doing things. This is done on every clock edge or during different state events like reset. But it checks the current state at the default at the beginning. The synthesized default is that these are the same. But then once the state machine's running with clock inputs, we have a case that says whatever the state is, go to that state. So if we're in idle, it goes to idle, and then it just if the go is a 1 or flag out is a 1, then it goes. Then the next state becomes the read state. Otherwise, it stays in the idle state. So that's what we're looking at here with this loop back. This one.
Right.
Right. So this translates to this little bit of Verilog right here. And then so the next state is read. If we're in the read state, here it is down here. So the next state is this read state. So in the read state, we've said here that the read output registered, which is the arrow equals, the read output goes to logic 1, the DS output goes to a logic 2, and the flag output goes to 0. I said logic 2, I meant 0. And so that's what happens here. We don't see any of those except next flag out assignment is done to 0, but we don't see any of the other outputs affected here. All we're doing here is the core state machine, and you'll see later on, and this is clean coding, right? So we have one very compact, well-defined state machine, and then based on the current state, we do other things in other parts of the code, right? So the next state would be delay. If there's a state transition, well, there's always a state transition here. You'll see read, we do this thing, we set the next flag output to 0, and then we set the next state so that at the next state transition it's always going to happen. So basically this is like saying, I want to be in this state for 1 full clock cycle, and then we're always going to this next state.
Right.
And so that next state is delay. So then we come up to delay. We set the flag back to 1, and then we check an input. If WS is a logic 1, then we can set the next state to read again. So this is some kind of serial input, you could say, and if we're constantly sampling a flag, WS, or an input, WS, if it's 1, we stay in that read, we go back to read. And that's the state transition we're looking at here. And then otherwise, after a delay, so the delay just makes us wait a clock edge. So it's like this, what we've defined here is kind of like you could say, it's reading and changing states to sample input bits on each clock edge, you could say. And then once WS is low, we're all completely done. So otherwise, in that case, the next state would be done, and then it goes back to done. and done just waits one full clock cycle and then goes to idle. So how else? So these are inputs that we're sampling here: go, flag out, WS, and we've set next flag out as an internal holding register. So that invokes a delay, and then we're assigning the outputs to certain specific bits from our state machine, and the read or RD output that indicates when we're in the read cycle or the read state. Otherwise, that output is 0. And then we get the actual control. So all of this is synchronized to a clock.
Right.
Right. So at first blush, you look at this and go, "Where's the pos-edge clock or neg-edge? Where's the code here to say this is all done synchronous?"
Right.
This is just our core state machine, but the actual synchronization comes here. So it adds this, and again, this is the clean, good coding style way of doing it. Always on a positive edge of clock or negative edge of reset. If it's reset, then we're going to set the state to idle and set the flag out to 0. Otherwise, if we're not resetting the whole system, so this is an asynchronous reset because we're treating reset as its own clock.
Right.
Otherwise, on the positive edge of clock, and we're not resetting, then we're using the clock to set the state to be the next state. So the state transitions are fully clock synchronous now. And the flag output is registered from the next flag output. And we also have the synchronous data path. So also asynchronous reset and reset of the outputs. Otherwise, we're on the positive edge of the clock. We're setting DS output to 0, setting the 2-bit reg DP out to 0, and then we have another case statement to say whatever the next case is. If the next state is going to be a delay, then we set the reg output to 0, 1. Otherwise, if it's done, we set the done signal or DS to 1. Otherwise, in every other case, DS is 0 and reg out is going to be 0.
Very cool.
Yeah. So basically, it does a really nice job of cleanly coding up a good state machine, and then of course you can take your code and do other things with the outputs or extend it. And VHDL, it's more lines of code for the same thing in VHDL, but it's essentially exactly the same structure. We use a case statement, which is very similar to case statements or switch statements in C. Case statements in Ada or Delphi, which is more like what VHDL is. And the processes are the same as our, always at pos edge clock sort of thing in Verilog.
Right.
We're 10 minutes over the hour. I didn't realize how long I was gas bagging on about this, but I really like this. This tool is very cool, and I think someone needs to get on their GitHub and do a pull request for adding the Perl script that generates the outputs in code just to the GUI would be cool. But another alternative would be, it would be cool to be able to write a state machine in Verilog or VHDL and actually import it somehow and have it draw the diagram for you. That would be even more useful, because to me the diagram is a documentation tool that helps you visually check your work and make sure you haven't left something out.
I just stuck it in the chat window to you.
Yeah.
Let's see. Would it define a new symbolic type in VHDL like type state type is, and then the parameters S0, S1, and S2 instead of a bit mask?
I don't know. I don't believe they've. No, they do. Yeah, it's more. So I'm showing this in VHDL. So they use these constants to do it. So this is like somewhat similar to a C define, I believe. So it's hard coding the actual state bit pattern into a constant, and they've defined a state type. So this subtype, this is a type definition, which is really just a standard logic vector. They didn't need to do that, but that makes the code probably more readable. Yeah.
Right. I saw the comment in one where it was like adding something like that allowed it to simulate with the state names in the simulation then.
Yeah.
That was at the bottom of the Verilog example.
Yeah. VHDL and Verilog both support most common language constructs like enums and things. So it's possible to do it that way, but people, I guess, in the code, it's been years since I've professionally coded VHDL, but I've never seen it. I've never seen those used for that. I see things like that are used much more in test benches for simulation, for driving simulation, because there's never any concern in a simulation test bench that some weird thing like a single event upset it with radiation.
Yeah, right.
I described before. That never happens in a simulator. So in your test bench, you can do weird things. VHDL, here's one example. VHDL has this keyword for an actual thing called transport. And it's a means of invoking a delay line. Right?
Okay.
But a synthesizer for an FPGA doesn't know what transport is.
No, I was going to say, right.
Because you have delays inside an FPGA, but you don't know what they are until after everything's hooked up. And so you can't tell it, well, I want a certain amount of delay. If there may be exceptions to that now, maybe since then there have been CPLD and FPGA manufacturers who've actually used up silicon space to create
a known delay
lines inside them. I can't imagine too many applications that require that.
Minimum delays are tough because the entire act of trying to manufacture the chip is to make it as fast as possible. So they would hate to throw away parts because they're too fast. If anything, you sell them for more, but minimum delays are tough.
Yeah. And where delays do get used and where they are actually made in silicon, it's usually part of a sealed block that you don't control in that granular way of a detail, like a delay lock loop, which is used for synthesizing multiple different clock frequencies. So you may have one master 50 megahertz clock on a Xilinx chip, but then you use the DLL, and in Altera they just call them PLLs.
Yeah.
But the delay lock loop is a digital variant of a PLL that uses different delay lines with taps. And you can multiply and divide based on where the taps are. But they don't, as far as I can remember, the FPGA synthesis tools don't allow you to specifically get under the hood and specify where the taps are and where the delay is, because it's mostly hard silicon. You can't really program where the delay hooks up. So things like transport aren't supported by synthesis, but they can be useful in a test bench to say, well, I want this signal and I'm going to emulate a delay on a circuit board trace while this bit comes down. So I have a clock, but then I have this bit, but the bit goes through a transport, and I want to see in my test bench and simulation how fast I can go before I start to get to uncertain areas or race conditions. So, yeah.
Right.
Yeah.
So, well, very good. That was a very cool example there. Somebody dropped the FISM, in the Discord channel, and now you get a demonstration of it. So,
Yeah.
yoo-hoo,
Yeah.
Discord. More.
That was a,
Come on,
that was a
come
great,
say hi.
yeah, it was awesome. That was a great thing.
Yeah.
Thank you. So I forget if it was Frank or maybe it was Nix who pointed it out. I'm sorry, I forgot specifically who, but
I forgot who it was
you know
too.
who you
Yeah.
are, and we're very grateful because this is a cool discussion, and this is a really neat tool, and I'm very likely going to start using this with my lattice chips that I'm playing with.
Cool. Cool. All right. Well, we have run past. We're 16 minutes past, so I'd say anything else to add before we call it.
No. There's always
somebody posted the disk drive manufacturer I was trying to think of was CDC. So yes, okay. It's one of those things. There's no way I was going to remember at my age, and we'll have to talk about things like what is gray code and stuff in a future show too. Then
yeah.
So very cool. Hey, Ben, my friend, good seeing you as always. Thank you, everybody that showed up and watched us here today. And again, catch us in Discord during the week, and we'll see you here next Friday.
Yeah, looking forward to it.